This is an investigation of the force between electric charges. Electrical forces are of enormous importance in nature. On the atomic scale, they far outweigh any gravitational forces. Electric forces hold atoms together and make steel wires strong. They also hold atoms apart and make, for example, water difficult to compress. I have here a tube which I'm filling quite full of water, and a piston which fits and will fall, just fits, it will fall slowly like that. It just fits. Now put this down on a squashy rubber sponge, let go, and give it a sharp crack with a mallet. Water is practically incompressible. In fact, electric forces hold the parts of atoms together, electrons and nuclei. If you want to understand atomic physics and really make much of the models of atomic structure that we use, you've got to know the law of force between electric charges. Scientists enjoy finding a law of force, not just for information, but because it adds to their general sense of understanding nature. It appeals to their sense of simplicity and reduces one more mystery to some form of law and order. We are going to investigate a universal law of force between electric charges. At small distances, electric forces compete well with gravity. Turn on my charging arrangement, please. Give a charge to the balloon. Collect a like charge on my balloon. They repel. At closer approach, more. Bigger force. Now, farther away, less force. Still farther, very little force. Now give an opposite charge, and I get attraction. What is the exact relationship between force and distance? You probably know already. Coulomb's law says force varies inversely as the square of the distance between the charges. That means that at twice the distance apart, the forces are a quarter as big, and at 10 times the distance, they drop to 100th. An inverse square law applies in many cases. For example, the illumination due to a small lamp, when light spreads out in straight lines through clear air, not in fog or muddy water that absorbs the light. Here are 3 books at so much, twice the distance, 3 times the distance from a small lamp. The inverse square law is characteristic of anything that spreads out in straight lines without getting lost. I think I can illustrate that with a fable. Suppose a restaurant has the problem of buttering toast and wants to be very modern and do it with a machine. So the proprietor invents a butter gun with melted butter in here, which can be squirted out in straight line spray of butter like that. Here's the piece of toast, and lines of butter go out and hit it there, and there, and there, and there, and butter it all over. Now, instead of that, lines might go on, and you could put the toast further back at twice the distance, 2 pieces of toast wide, 2 toasts high, and altogether you would put 4 pieces of toast there to intercept the butter, and you'd be half as thick, no, quarter as thick buttering. Inverse square law. At 3 times the distance, 3 pieces of toast, 3 pieces of toast, altogether 9 pieces of toast, and you would get 1/9 of the buttering economy treatment. A century after Newton guessed at an inverse square law for universal gravitation, Coulomb guessed at a similar law for electric forces. He tested his guess with a torsion balance, rather like the Cavendish apparatus used for gravitational inverse square law test. Here it is: fiber, twisting beam, two balls to carry the charges. In our experiment, we shall use a spring balance to measure the force. Like that. Two metal balls that we can charge up, a beam carrying one, and a spring to balance the force between the balls. And over here, a pointer which will show the stretch of the spring on this scale, and that gives us an estimate of the force. I'm going to ask my assistant to take the upper ball away, and we can see if the zero is correct. I should like you to see how sensitive this is. I have here a box of weights, 1 gram, that's too big, 1/10 of a gram. I'm going to ask you to put on 1/10 of a gram on the ball, please, and we'll see what that does to the scale. Now first, let's settle the zero. First, just wait while I settle the zero. I'm tapping the balance to free the bearings. Starts with a zero. There, about there. Now put on 1/10 of the gram. Load it up. 1/10 of a gram is within 2%, 1,000th of a Newton. And you see it's going to settle down very close here to 10. And so each of these scale divisions represents 1/10,000th, roughly, of a Newton force. Take the load off, please. Now I shall show you how we measure the distance apart of the two balls. We move them till they're 1 span apart, or 2 spans apart, like that. I'm going to call each of these distances a span, though in fact you will see that they are pretty well 15 centimeters each. 15, 30, 45, but we shall not use those numbers in our experiment. I shall just call them 1 span, 2 spans, 3 spans. Here is a record. We shall have distance apart and force, and we shall run from 1 span to 2 to 3. We shall start with one ball far away at infinity, and like this. And then at infinity, the force is going to be 0 because we'll start the pointer there. Then we shall start 1 span. First, I must charge up both balls. I'm not going to explain this ancient device for charging, except just to say that it operates by induced charges on the plate that I'm carrying. I think that will be perhaps a little more. Sufficiently charged. Now, please set the balls 1 span apart while I look at the scale. There we are. Force is at 1 span, please record it, between 23 and 25. It's just about 20. Settle down, it'll be 23.7. Now 2 spans, please. Oh, force is much less. Well, what did you expect with an inverse square law? Still further up. Encourage the pointer to stop moving. Then we have 5, 6, 4.8, 5, between 4.8 and 4.0, about 4.4, please. 5.4, sorry. Thank you. Now move to 3 spans. Still smaller force. 3, 2, 2.903, about 2.5. 2.5. Now let's see what that record tells us. When I go from 1 to 2 to 3, an inverse square law makes the forces go down from so much to a quarter to a ninth. And we can test for that by multiplying them by 1 and 4 and 9 to see if we get constant numbers. 23.7, we'll call 23.7, 24 will be near enough. 4 4s are 16, 4 5s are 20, 21.6, say 22. And 9 5s are 45, 9 2s are 18, and 22.5, 22.5. So that I get very closely the same number. Actually, I expect less, because charges leak away along imperfect insulators. And the third measurement is too small to be reliable anyway. The inverse square law is a great general law of force. And to be sure of it, you would have to take a whole variety of experiments over a wider range of distances, with attraction as well as repulsion, with different apparatus, and with different charges. You would find no exceptions, other than those due to difficulties of apparatus or leakage and things like that. And then you could trust the law for ordinary sizes of apparatus. And you might let the atomic scientists extrapolate it down to atomic sizes. That's the risk we always have to take in atomic and nuclear science. We assume that the large-scale laws apply, and we test them if we can. Actually, we can test the inverse square law inside an atom, and we find that it does hold there. And now, what happens if we change the charges? I'm going to use a trick to change the charge on one ball. I'm going to bring in an extra ball of equal size, uncharged, touch one ball with that, then when they're together they make one conductor, and symmetry tells me the charge will be shared 50-50 between them. Take away the extra ball and give its charge to ground, then here I shall have one ball with half the original charge. Now let's try that. Here is a spare ball of the same size that I can share charge with that ball with by touching. First of all, let me just look at my 0. See how that looks. Not quite. There. Now, let's charge up both balls, please. Set them one span apart, please. Nearly there. Now this measurement you're going to have to remember. I shan't write it down, just remember what it is. It's just above 18, between 18 and 19, just above 18. Now, swing out the ball, please, and we'll share 50-50, and